Every single year, 37 million people are injured from falls, and almost 700,000 people die. Falls are the leading cause of death in construction, with almost 40% of all deaths in construction coming from falls, according to OSHA. The goal of my project is to create a climbing robot that is able to help prevent these injuries and deaths. The most common method for preventing these falls in a work environment is a harness to catch someone in the event that they fall. Now, the issue with this method is that for that harness to be effective, the rope that you're attached to on it has to be anchored up at the height that you're working at. And for that to happen, someone either has to use a big heavy machine like scissor lift or cherry picker kind of system to carry them up to install an anchor, or they have to free climb up there, essentially climbing up without any actual protection. Other climbing robots do exist, but they exist as their own independent system, separate from bringing a human up to it, and they are also often highly specialized, only designed to perform one task, if anything, on top of just being able to climb up to heights. The design constraints for this project were that it should be able to climb up a wide variety of surfaces, for this prototype defined as a ladder and a flat rock wall. And it should be able to hold a minimum of 100 kilograms with a safety factor of 2. It should be able to serve as a base for future parts to be built on it, such as, say, a drill for collecting samples, or an arm with a welder for performing tasks like wind turbine repair, something that other parts can be easily placed on. It should also be able to act as an anchor point and be able to catch a person if they are falling, and it should be cheap and cost-effective. The basic idea for this robot was essentially just a tube that is able to extend one side out and then pivot itself around to be able to climb. So it would basically just be a tube that has an end effector on either end. It's able to grab on to a hold, pivot itself, grab onto another, release the first one, pivot again, and then it can change its length if needed. I then took this basic concept and used the 3D modeling software Onshape to create all of the parts and to work out the details, eventually creating this final model for the robot. The extending part has a total travel length of 18 inches. The actual travel is actuated by this linear actuator, and the pivot is connected primarily to this rail here. It goes through the main body when it is fully retracted, kind of telescoping, and it is a hardened steel for the main rail part here, keeping it strong enough so that when it pivots, it is actually able to take the full load. The rail is guided on the inside using 2 carriage blocks, and it has a wheel on the bottom that slots into it, like that. There are 2 of these setups with the carriage blocks, and these wheels here help to keep it from rotating too much. It was far more cost-effective to use this type of rail that's able to have some side-to-side motion than one that doesn't. And so these wheels I used to make sure that the side-to-side motion didn't have too many negative impacts. This right here is the whole pivot and end effector assembly. It is what pivots the main body around to allow it to climb, and it's also the part that grabs on to any holds. This motor here is what drives the actual pivoting. It's connected to a custom planetary gearbox here that is 3D printed using nylon filament on the inside to give it enough strength and heat resistance. It's about a 70-to-1 gear ratio to give it enough torque, but even that's on the low end, and ideally it would be slightly higher. And then the whole thing is mounted to this right here, which is free spinning, so that when the main shaft spins, it is able, the end effector doesn't have to rotate, and it can stay clinging onto the hold while the whole main body rotates around it. And then this part here, you can see with the actuator, and this here is the actual end effector, the part that grabs on. It's driven by a 3,000 Newton linear actuator, terrifyingly strong, and it basically just clamps down very hard on whatever hold you need. It is designed to be modular, or like a quick swap, so that with only a couple of bolts, you can pull out these little end bits here and swap them out for a different one to suit whatever terrain you're trying to climb on. So for example, these here, the first one that I pulled out is just a flat one like this, or like one with a silicone rubber on it, are the ones that I tested for uses on things like climbing ladders, and those worked rather well for smoother, flatter surfaces to increase the friction. But ones like this, which feature, which is a spine cell, or basically it has a bunch of little spring-loaded needles to catch small asperities in surfaces, or little imperfections in rocks and natural formations. These are much better suited for natural climbing environments. Now, one way that I tried to cut down on costs with these was, instead of trying to have something custom manufactured, I discovered these stainless steel tapestry needles that were the exact size that I needed, and used these instead of trying to custom manufacture spines or wool needles. But yeah, these work perfectly well to catch into small imperfections in surfaces and really increase the friction on it, which gives it a much stronger hold. Now, this whole assembly, it just clamps down on the surface. You can quickly swap them out, and that's kind of the rundown of the whole robot. The main things that I found with the end effector in the robot are that the end effector needs to be built with some slightly stronger materials, ideally. These plates here, in my initial testing, I only had one. It immediately just bent the plate to 90 degrees the second I tried to close the actuator around something. So I had to double it up like this, using these to increase the strength, and this did worlds better, but it still started warping after a certain amount of force was applied. So ideally, it's only mild steel, and ideally it would be hardened or a stainless. And then just these blocks could be some stronger material, ideally. Mostly just some simple material changes that would mostly just affect budgetary constraints. And that I spent on this was around $400 of materials, and with all of the changes that would make this fully ideal, or like for more of a kind of a final product, it would probably bring it up to only around $750. Yeah, at the end of the day, this robot was able to accomplish all of the goals that I was hoping for it to, and I think it serves as a great proof of concept and prototype for something that could help save a lot of lives and prevent a lot of injuries in the future.